Hey everyone, this is question number 76 from chapter 6. This problem is about an elevator falling and there's a spring at the bottom of the elevator shaft. All right, so part A asks us to find the work done by gravity. So work equals force times distance. Force of gravity equals mg and times d. And then d is going to have an angle of cosine of 0. Gravity's pulling down, the motion's down. Cosine 0 is 1, so that makes sense. So then the work of gravity equals mass, which is 925 kilograms, times g, 9.8 meters per second squared, times distance, which we're given is 28.5 meters. Plug all that in, and you get work equals 2.5835 times 10 to the 5th joules, which we can round, or we can use sig figs with to get 2.58 times 10 to the 5th joules. That's part A, work done by gravity. All right, part B asks the speed just before the elevator hits the spring. All right, so to do that, work equals change in kinetic energy. And we're going to assume that that the elevator dropped from rest. So we have work equals final minus initial, 1/2 mv2 squared minus 1/2 mv1 squared. Saying initial velocity is 0, it's dropping from rest. So we have work, we have all the rest of this, we can solve for v2, or for v. So v right before it hits the spring equals the square root of 2w over m. Plug in numbers, square root 2 times 2.5835, that's a 3, times 10 to the 5th joules, all over 925 kilograms. Plug all of that into your calculator and you get 23.6 meters per second. All right, so the last part of this question asks us to find the amount that the spring is compressed. Okay, so in order to do that, we need to think about what two things are doing work here. All right, so work in this equation is done by gravity, which is down in the direction of motion, which is down in the direction that the spring is going to compress. Okay, and then we also have work done by the spring, and the spring is going to be pushing back up against the spring is going to be pushing back up against the elevator in the opposite direction of motion, so it's going to be minus work of the spring. Okay, and by work energy theorem, the net work done has to be equal to 0 because the object, the elevator that we're talking about, ends at rest. Okay, so 0 equals Wg minus Ws. All right, so we can go ahead and start solving here. Wg we just found is going to be equal to mg. So 0 equals mg. Okay, and then we need distance here though, and we know that gravity is working the distance that it falls, but we need to know how far it also compresses, and gravity is going to work that whole distance of compression. So our distance for the work of gravity is going to be d that it falls plus that compression distance that we're solving for. Okay, and then minus spring work is 1/2 kx squared. And again, x is what we're looking for. All right, so we can expand this a little bit and get a kind of nice quadratic equation. We're going to add this over the other side so we don't have a negative starting coefficient. So 1/2 kx squared minus mgx minus mgd equals 0. All right, and that's just adding everything over, adding this over the other side, distributing the mg to the d and the x, and then subtracting those over the other side. All right, so then we can do quadratic equation. Just as a reminder, quadratic equation, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So plugging in these as coefficients, we are going to get x equals mg plus or minus the square root of m squared g squared minus 4 1/2 k times minus mgd all over 2 times a. Okay. All right, and that is going to simplify a good bit. All right, it's actually, that doesn't simplify. Well, you can simplify the bottom. This will become just k. But we can go ahead and plug in numbers. I'm going to go to another page because this is going to be a really nasty equation. But we get x equals 925 kilograms times 9.8 meters per second squared plus or minus the square root of 925 kilograms squared times 9.8 meters per second squared plus or minus, I'm sorry, not plus or minus, just plus 2 times 9.8 meters per second squared times 8 times 10 to the 4th Newton meters times 925 kilograms times 28.5 meters. Okay, so just to make this clear, this is all multiplied together. I ran out of space. This is a big square root. And then all of this is divided by 8 times 10 to the 4th Newton per meters. And that's going to give you a value for x, maximum compression of 2.65 meters and minus 2.43 meters. And we assumed that x was going to be greater than 0. We just added on this extra distance. So the correct answer here, the maximum compression is going to be this one. It's going to be the positive value, 2.65 meters.